I want to look at what's called the standard Euclidean metric on R2. So I'm going to, when I say R2, by the way, I just mean the reals cross the reals. And just to be very, very clear, this is just the familiar XY plane. And I actually want to talk about the familiar notion of distance that you're used to. If I pick 2 points, then I literally want to write down that distance, this distance between them, in the way that we're all familiar with. I'll say it again, though. There are other ways to define distance. We'll look at another one in just a moment. So the standard way of defining distance is if I have one point is x1, x2, the other point is y1, y2. Sometimes you might have been used to writing this like x1, y1, x2, y2. I'm not doing that here, right? My y coordinate in this case is x, and my x coordinate in this case is a y. Whatever, we can handle that. So this is the the distance between these 2 points is defined as the square root of x1 minus y1 squared plus x2 minus y2 squared. It's exactly the same distance formula that you've used and worked with since you were a wee child. And so you can check, I'm not going to do it, but you can check that this is a metric on R2, and it's called the standard Euclidean metric. I want to say just a word about this. So this metric generalizes. You can do this in R3. If you've had Calc 3 already, then you know we have a similar distance formula in 3 space, and you can do the same thing in 4 space or 5 space or 10 space or a billion space. This metric works in space, and it's always called the standard Euclidean metric on Rn in general. One other quick little comment I'll squeeze in here. When we're talking about R1, which is just the reals, then our standard metric, D, of 2 real numbers, x1, you know what, I'm going to use A and B just to try to have clear notation. This is the absolute value of A minus B. Please realize that's the square root of A minus B squared. It actually fits the same formula as the same metric we're doing before. So I just want to make sure that's clear to you. Is it's the same metric. The same metric that we've worked with over the reals generalizes to this metric, and they're actually defined in the same way. We think about this one differently because we could just do it with absolute value, but absolute value is defined as the square root of the thing squared. So don't miss that connection. Okay, let's look at a little different metric. This is called the Chebyshev metric. And again, we're going to work over R2. So we're going to be working in 2 space, which you're familiar with. But I want to define distance quite differently than what you've seen before. And so how does it go? Well, we define D by the distance between 2 pairs of points, x1, comma x2, and y1, comma y2. This is defined as the max of the following set. And so the first set is x1 minus y1, and then the second element is x2 minus y2. So you compute those things, you take the largest of the 2, if they're the same, that's fine, and that's the distance between your 2 points. And so this guy, let's just say, is a metric. I'm not going to verify the 3 properties here. I did think I would do just a quick example with you. So let's figure out what's the distance between 2, 3, and 4, 1. Like we can plot those points, right? X is 1, 2, y is 3, x is 1, 2, 3, 4, y is 1. And so we want to know what's the distance between these 2 points. Not this distance, right? That's the Euclidean distance. What's this new distance under the Chebyshev metric? And well, what is it? It's the maximum of the absolute value between 2 and 4, and then 3 and 1, 2 minus 4, and 3 minus 1. And you take the max of those 2. This is just the max of, 2 and 2, which is just 2. So the Chebyshev distance is 2. So I'll stop this video here, and we'll go on to the next part.